Okay, today we're going to talk about the different representations that we use in chemistry. This may seem obvious, but it's good to keep in mind the different kind of representations that chemists we use depending on what they mean. For example, when we think of water, uh, regular people, not chemists, will think of like a glass of water, what we drink, what 70% of the planet is made out of. That's called a macroscopic representation. However, chemists use a different kinds of representation. One, as you can see on the right here, the water can also mean how the molecule of water is connected. These balls would represent the atoms and how they bound to each other. And a third kind of representation, it's what we call the symbolic representation, in which only the ratio of different elements are represented in a formula. And for example, in a reaction, that would also be the symbolic representation. So here we have then three different kinds of representations that we use in chemistry: the symbolic, the macroscopic, and the atomic, also known as submicroscopic. The macroscopic is the representation. Actually, it's just more of an experience that we see in the lab. It smells, we can touch it, we can measure it with microscopic instruments. There's also a more qualitative, and that's important, it's qualitative representation of molecules and atoms, and that's what this picture here represents. And this the symbolic representation that sometimes, as we will talk about in the next slide, may refer to either macroscopic representation or atomic. So when we see H2O, we may mean the liquid phase or the ice or the vapor, or we may mean the actual molecule. These two, of course, are very different, the atomic and the macroscopic, and the symbolic may represent those two, depending on the case. So let's give you an example. For example, if we see this is a clear symbolic representation, H2OL, that means water liquid, becomes water solid. Okay, so water liquid becomes ice. This is definitely refers to a macroscopic event, even though we're using the symbolic representation. Something different would be if we write H2O becomes H plus OH negative. Now, notice that there is no phase associated to here. This is one single molecule in which a hydrogen breaks the bond and becomes an isolated, in this case it's just a proton, a positively charged hydrogen. Okay. In this case, the symbolic representation is used to represent atomic event or a submicroscopic event. If you need another example, it would be, for example, sodium chloride, table salt, dissolved in water. The moment we talk about water liquid, liquid is macroscopic. One single molecule of water is not liquid, nor solid, nor gas. Those are macroscopic events. Okay, so this reaction would be, even though it's expressed in symbolic representation, it refers to a macroscopic event. Different would be if it's a molecule of sodium chloride interacting with one molecule of H2O, in which there is a specific bond being made. That's, again, it's a submicroscopic or atomic representation. Okay. Hopefully you're familiar, or you remember from the organic chemistry that you took some time ago, that the symbolic representation, such as, for example, 1-chloropropane, in this case this is a symbolic representation, but it starts having a little bit of a flavor of a atomic representation, because even though we're using a symbolic representation, we are also indicating where the atoms are connected. Okay, so please keep in mind that in organic representation, the difference between symbolic and atomic representations are fuzzy. Okay, I'm going to draw here different representations of 1-chloropropane, and all of them are the same molecule, but this one, for example, down here is definitely an atomic or submicroscopic representation, but maybe not that different from this one down here that we would refer as symbolic. Okay, hopefully that makes sense, and we'll stop here, and we're going to move on to new topics in the next video.